There are a few different techniques that we can deploy to solving exponential equations, and it really just depends on the setup of the original problem. The first and probably easiest scenario is when we have exponentials on both sides of the equation and the base of the exponential is the same on both sides of the equation. In that circumstance, for these two sides of the equation to indeed be equal to each other with the same base, that means you have to have the same exponent. So we can essentially just forget about the bases and then just take those exponents and set them equal to each other. So we've got 7x minus 1 from the left-hand side has to be equal to negative x plus 7 on the right-hand side. Again, this technique only works if the two bases are identical, which in this case they are. And so then we just end up with a pretty ordinary equation where we're just going to add x to both sides. And so we end up with 8x minus 1 equals 7. And so then we can move the 1 to the other side. And so we get 8x equals 8. Or if we divide both sides by 8, we get x equals 1. And so if we go back and plug 1 into the equation for x, we'll see that we'll end up with the same exponent on both sides. If we plug in 1 for x on the left, we're going to get 5 to the 7 times 1 is 7, minus 1 is 6. And on the other side, if we plug in 1 for x, negative 1 plus 7 is also 6. So we can see that our answer of x equals 1 works. For the second example, again, the base is the same on both sides. It's e to the 6x on the left, it's e to the 3x plus 10 on the right. So in this circumstance, we can just forget about the e's and set those exponents equal to each other. So we've got 6x on the left, 3x plus 10 on the right. So this time we'll just subtract 3x from both sides. So we get 3x equals 10. And so then our last step is to divide both sides by 3. So we get x equals 10/3. So this time we won't bother to check. But again, the idea of the approach is the same. We can go ahead and just eliminate the bases and set the exponents equal to each other. But this only works if we have the exact same base and just a single exponential on both sides of the equation. Some exponential equations have exponentials on both sides, like what we see here, but they don't have the same base. But we can make them have the same base. So we can eventually end up with where we were in the previous two examples. Right now we have 4 to the 3x on the left, we have 8 to the negative x plus 1 on the right. Hopefully we recognize that 4 and 8 could be both rewritten as powers of 2. So what we can do is we can say instead of 4, make it 2 squared that's being raised to the 3x power. And then on the other side, 8 is 2 cubed. So I can do 2 to the 3rd. That's going to be raised to the negative x plus 1 power. And so then we can take advantage of our rules of exponents that says when we're raising a power to a power, we're going to multiply those exponents. So on the left-hand side, I'm going to end up with 2, and then 2 times 3x is going to be 6x. And then on the other side, I'm going to end up having to do a little distributing when I multiply the two exponents together. So I'm going to end up with 2 to the 3 times negative x is negative 3x, and then 3 times 1 is 3. So now we're in the same place as we were on the previous examples, where we have a single exponential on both sides, and we have the same base. So now we can go ahead and forget about those bases and set those exponents equal to each other. So we have 6x equals negative 3x plus 3. Add 3x to both sides, and so we get 9x equals 3, and then if we divide both sides by 9, we just have to be careful, we end up with x equals 3/9, which reduces to 1/3. In the second example, we have the same sort of circumstance. We have a single exponential on both sides. As of now, we don't have the same base, but we can get there. So I'm going to rethink this 27 as being 3 to the 3rd power. So I'm going to write this as 1 over 3 to the 3rd to get started, and then being raised to the negative 2x. And then on the other side, 9 can be rewritten as 3 squared. So that's going to be 3 squared to the 2x minus 1. Now the challenge I have on this side over here is that the base that I have, the 3, is in the denominator. But another rule of exponents that we hopefully remember is that I can move this base to the numerator and then just change the positive negative sign of the exponent. So 1 over 3 to the third is the same as 3 to the negative third. So I can move that base up to the numerator, but then I have to change the positive negative sign on the exponent. And then of course I still have that negative 2x exponent on the outside of the parentheses. Then on the other side, we can go ahead and leave it for now, this 3 squared to the 2x minus 1. So now we're ready to use our rule of raising an exponent to an exponent, meaning that we're going to have to multiply. So I'm going to multiply here, so I end up with 3 to the negative 3 times negative 2x is positive 6x. And then on the other side, I have a little distributive property that I have to do in my multiplication. So we're going to end up with 3 to the 2 times 2x is 4x, and then 2 times negative 1 is negative 2. So now we finally have both sides with the same base, so we can now set those exponents equal to each other by just eliminating the bases. So we've got 6x equals 4x minus 2. So I'm going to subtract 4x from both sides. I end up with 2x equals negative 2. So my last step is going to be to divide by 2. And so we end up with x equals negative 1 as our answer. In equations where we have just a single exponential or a mix of a single exponential and multiple non-exponential terms, then we're going to have to use logarithms. Because the challenge is we have a variable inside of the exponent and no other mechanism of getting it out from the exponent. So the first thing we have to do is isolate the exponential. So in this first example, we've already got that. We've got 9 to the 2x plus 3 is isolated, and then we've got the 30 on the other side. So now I'm going to rewrite this in logarithm form using our pattern. So recall that for a statement b to the x equals y, that can be rewritten in long form as log base b, so the base of our log matches the base of our exponential. The output of the exponential becomes the input into the log, and then the exponent gets isolated on the other side. So applying that to this example, I'm going to have log base 9, so the base of my log matches the base of my exponential. The output of my exponential becomes the input into my log, and then it's going to equal the exponent, so 2x plus 3. So here we have succeeded in getting the x out from being in the exponent and is now on the other side of the equation. Now, we've got a regular equation at this point, just with this log base 9 of 30 over here. So this is a number that we can use our calculator to calculate, and then we can get about subtracting 3 and dividing by 2 on both sides. But we first have to use our calculator to figure out what the log base 9 of 30 is. And so if we don't have a calculator that allows us to enter whatever base we want, we have the change of base formula. So I can change this to base 10 logs, and so I can rewrite it as log base 10 of 30. Remember, the input into the log goes in the numerator with the new base, and then the log of 9 in the denominator. So the base goes in as the input in the denominator. And then that still equals 2x plus 3. So now we can use our calculator to figure out what does log of 30 divided by log of 9 equal. So using our calculator, we find that if we take log of 30 divided by log of 9, we get 1.548 if we round off to the nearest thousandth. And so then that equals 2x plus 3. So now we're in ordinary territory. It's just we have this decimal number that's hanging out in our problem. So I'm going to subtract 3 from both sides. So I can use a calculator to help me get negative 1.452 as the answer, equals 2x. And then my last step is to divide both sides by 2. And so then we get x equals negative 0.726. So again, the only way that we're going to get our variable out of the exponent in this circumstance is to rewrite it in log form, because that's going to get the exponent isolated on the far side of my equation, and then I just have to use a calculator along with the change of base formula to evaluate what that logarithm equals, and then use my regular two-step equation solving techniques, subtract the 3, divide by 2 in order to solve. For the last example, before we start rewriting it in log form using the pattern that we have here, we first have to isolate the exponential. So we have a little bit of preliminary work that we have to do. So I'm first going to subtract 8 from both sides. So I've got negative 2 e to the 3x equals negative 40 minus 8 is negative 48. So then, before I rewrite it as a logarithm, I need to divide both sides by negative 2, so I have to fully isolate the exponential. So now I have e to the 3x equals negative 48 divided by negative 2 is going to be 24. And so now at this point, I have the exponential isolated, so I can use my pattern here to rewrite this in log form. So the base of my log, or exponential, becomes the base of my log, so it's going to be log base e, which of course we never write. Instead of writing log base e, I'm going to immediately just write that as ln. So I'm going to use that ln to describe log base e. What my output of my exponential is going to become the input into my logarithm, so that's going to be 24. And then a logarithm is an exponent, so the exponent in my exponential here is going to be isolated on the other side, so I end up with 3x isolated there. And so now I'm ready to move to my calculator. I use the ln key to find the natural log of 24, and so we get 3.178, again rounding off to the nearest thousandth, and so that still equals 3x on the other side. So then our last step is to divide both sides by 3, and so we get x equals 1.059. So again, on this one, we had to do a little preliminary work to isolate the exponential, but then we use that same pattern here of rewriting the exponential as a logarithm, which is what got our variable out from inside the exponent and on the other side of the equation. So then we just used our calculator to help us the rest of the way.